Organizing Secretary and Co-Principal Investigator CAST, and Professor of Soil Water Conservation Engineering, MPKV Rahuri. Dr. Sachin Nalode, Joint Organizing Secretary and Member of CAST and Head Department of Farm Machinery and Processing Engineering, MPKV Rahuri, all training coordinators, and my dear participants. It is my privilege to welcome Dr. Qin Zhang at this occasion, and I take this golden opportunity to introduce today's expert speaker, Dr. Qin Zhang. Dr. Qin Zhang is a professor of agriculture automation. Dr. Zhang's core research interests are in creating technological solutions for automated agriculture production. His research activities include advancing agriculture machinery from manual center for precision and automated agriculture system, manual to auto-implemented, and all the way to autonomy, integrating information management and system optimization on machinery to make them intelligent machines, developing agriculture robotics technologies, and studying the cybernetics theory. He has published more than 180 articles in peer-reviewed journals, H-Index 46 on Google Scholar, authored 3 textbooks, and edited another 3 technical books. On his record, the 12 book chapters are also reported. He has 11 awarded US patents. He is editor-in-chief, Computers and Electronics in Agriculture. He is a full member of Club of Bologna, Strategies for Development of Agriculture Mechanization. Dr. Zhang is also a fellow of American Society of Agricultural and Biological Engineers. Now, I welcome Dr. Zhang and request him to deliver a lecture on agriculture robotics, the need, impact, and strategies. Thank you very much.
Thank you very much, Dr. Farhande sir, the convener, for introducing Professor Zhang. I would like to request Professor Qin Zhang, Professor and Director, Center for Precision and Automated Agriculture System, Washington State University, USA, to start your lecture and presentation.
Okay, can you hear me now?
Yeah.
Yes, sir.
Okay, so I will try to load my slides. Let me see. Share. So can you guys see the slides?
Yes, sir.
Yes, yes.
Okay, let's go. Here we are. First of all, thank you very much to have me to give this talk. I'm really excited and honored. Okay, and I also feel a little bit pity. I was, had a chance to visit your university later last year, but because of some issues, I was not able to go. I wish one of those days I will still have the chance to visit you guys. The topic of my presentation today is agricultural robotics, the need, the impact, and the strategy. Before we, let me see how it goes. Looks like I'm stuck here. What do you see on your screen? Looks like my screen is stop.
Yes, sir. It has stopped.
It's stopped. What do you see in your screen?
First slide.
It's the first slide.
Yes.
How can it not move? Okay. Okay, it moves, right? Okay, now looks like problem solved. Well, before talk about agricultural robotics, and let's have a quick review on what is the purpose of agriculture. In the past 30-some years, I have gave lectures at more than 60 universities worldwide, and including many departments in like in computer sciences and robotics institute and many of non-agriculture departments. In these places, I told them, agriculture. Many people think agriculture is kind of low tech, I told them probably it's not quite right. And agriculture is a very old industry. That's true, but it might be the the only industry it will last forever. Let's thinking about as I told them. Let's assume one day if we do not have a cell phone, can we still alive? Another day, we may out of a computer, we may out of internet. Can we still survive? Life might be hard, but I would say, the human being can still survive without it. But on the other hand, let's thinking about, how about if we do not have food? How many days we can last? One day it's okay, maybe. 1 week, I'm not sure. But for 1 month, definitely everybody will gone. So agriculture is the essential industry in this world. It can have, this world can have no industry for mankind, but it cannot survive if without agriculture, because it provides human being the food, the fiber, okay, and also the feed and the fuel and so forth. So people often say it's agriculture is for 4 F's, but the bottom line, agriculture is for food. And another feature of agriculture is it is a highly localized industry. The agriculture in US could be, it's not could be, I'm pretty much sure it's totally different from the agriculture in India. Okay, even in US, agriculture in Washington is completely different from agriculture in Illinois, where where the state I lived there for over 20 years, and I know there quite well. And I compare these 2 states. I find out that agriculture in these 2 states are completely different. Let's just look at the Washington state as an example. Washington state is agriculture is very diversified. It grows more than 300 different commodities. Okay, with the revenue, this number is about 3 years ago. Today, the revenue is more than $11 million US. And out of those 300 different commodities, the top 5 commodities are apples, milk, cattle, potato, and wheat. And the 5 of those top commodities counts for more than 50% of the revenue from Washington agriculture. Okay, that's the second factor. The third factor, I would say probably, at least in the percentage per se, probably will be could be fairly similar to Indian. More than 95% of our farms are family owned. Only about 5% are owned by companies, big farmers. Okay. And why I list this as one of the feature, later on we will see. The family-owned operation could affect the adoption and the adaptation of robotic technology. And the next very important challenge in facing American agriculture especially in the Washington agriculture, is a labor shortage. Because I have never been Indian so far, so I have no idea if Indian also experience labor shortage. But I do, in China, many times, and in as a part of a, world, many times, and most of the countries I have been, labor shortage or farm labor shortage is a common issue. Okay, and this labor shortage is basically the driving force for having robotic technology for agriculture. And then look at why the labor shortage come from. And you look at the past 110 years in US history. The farming population change over the past 120 years, actually, because I do not have a 2020 year data yet. I think that data needed to be available by next year or the year after. So far for the every 10 years data, I can only stop at 2010. We look at back in 1900. In US, the urban population is about 40%, and the rural population is about 60%. Again, I'm not quite sure, for the Indian situation today. Maybe it's quite similar to this percentage, because I know many of the, the break 5, break 4, break 5 countries are basically, based on what I heard, is basically in this level today. And then, as the industrialization and the urban population keep increasing, and the rural population keep decreasing, and that affects the farming population also, decrease quickly. For example, after 50 years to after World War II in 1950, the urban population is almost reached 2/3 of the US population, and then only 1/3, a little bit more than 1/3 living in rural area. And among that, it's less than 25% population is working as, is a farming population. So in 70 years ago, in US, it's still about, okay, I look at it 1 year. It's 70 years ago, in US, it's only 15% of population is working as a farmer, is doing farming operation. And then as the trend continue going, and to the, turn to the new century, year 2000, US population is about 80% living in cities, only about 20% living in countryside. And among this 20%, the population really doing farming work is only about 1%. So this is why the labor shortage in American agriculture is a #1 challenge. And to address this challenge, the only solution is mechanization. However, even mechanization, it still need human labor to drive it. So the next step of mechanization is the automated mechanization. Used as a word is the robotics. So the need for robotics is because of the increasing the pressure of labor force shortage in the field. Okay, that's the #1 challenge. And the second thing is also very important. And it makes agricultural robotics very unique. Many people think industry robotics is already developing into a very high level. Okay, so we just try to adapt industrial robotics to solve agricultural issues. Should be easy. But the reality is that's not true. Because agricultural operation is so complicated, it makes today mature technology for industrial robotization will not work in agriculture. Among them, one of the challenges is most agricultural operations are highly seasonal operations with a very limited time window. What does that mean? That means if we build a robot for a particular operation, that robot can, very likely that robot can be used only in 1 to 2 weeks for a year. And the rest of the time, that robot is useless. That makes a lot of challenge. For those challenges, what are those challenges? I will address that in later. And then another thing, why it's so difficult? And then looks like it will bring too much challenge for robotics, right? But however, it also gave us a big opportunity for use robot. The opportunity is if you look at the agricultural operation, when you're doing farming work, you will find out most of those actions the farmers are doing are highly repetitive. They're basically repeating doing things again, 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 and again. So this repeating provides a very good application case for use robotics. So for the robotic technology, it's the research and development for robotics technology itself. You can trace back to more than 50 years. As a matter of fact, as soon as people started the industrial robotic technology research, some people started the study or the research and development of agricultural robotics. So for the agricultural robotics research, the history is almost the same as industrial robotic research. But after 50 years, you may see industrial robotics has gained fairly wide applications. Okay, and today you can see some of the shop floors. There's no human work in there. Everything is done by machine, by robot. But today, you can see very few robots being used in the field for doing agricultural work. Is that mean the technology is not there yet? The answer is no. Technology is there. Here I will give you some examples. The first example, you look at this tractor, it's pulling a planter. And if you pay a little attention to the cab of the tractor, you may see there's no human driver in the tractor. Okay, and the tractor can go, the tractor system can go to the field autonomously. And then when doing getting the right position, you can see it lower the planter and speed up doing the autonomous operation automatically. Okay, and then when go to the end of the field, it can raise the plant and turning around and then do it again. And after it's done, the tractor can also find its own way back to the garage and shut it down automatically. Is this research very new? Nope. This is a tractor we developed in more than 20 years ago. This video footage was shot in 1999 at the research farm for University of Illinois Urbana-Champaign. And why the technology is there for more than 20 years? Can we see such tractor in the field today? Answer is also negative. No. Why not? There's some other issues. And this basically is the main topic of today's presentation, why agricultural robotics are still facing some issues before we can widely adopt it. The second, this technology is also developed more than 20 years ago by my group in University of Illinois Urbana-Champaign. And when you look at it here, this is the mechanical cultivation operation. Okay. And we can restart this video again. And when you restart, before you're doing the cultivation, you may see the weed is covered the field. Okay, and even human eye can hardly distinguish where the row crop rows, where's wheat. Okay, look at it here. Can you easily see where's the crop and where's wheat? Using human eye is very difficult. Of course, you pay very close attention, you can see it. But if we use sensing technology, we can find out the reflectance to the sunlight from the crop leaf and from the wheat leaf could be different. Okay, so that means if we select right sensor to sense the light reflectance in certain wavelengths, the sensor, you can make the sensor can only see the crop rows and ignore the weeds. Therefore, you can use that sensor to guide the tractor following the crop rows very precisely without damaging. And so this provides the robot a better capability than human eye to distinguish that. So here gives another very important point, which is the robotic technology sometimes can do in general, we say robotic is not as smart or not as capable as a human being. But for some particular applications, just like to detect the crop row, the sensors could provide better performance than human being. So that means the robotic, for some particular task, the robot could do a better job than human can do. This gives us another opportunity to utilize robotics in agriculture. Okay, and then this example gives another very interesting example. This is a robot we built. The researchers at CPAS built for the growers nearby our center. And many of you may do not know what this is for. And if you look at the background, I do not know how many of you have seen a crop called hops. Maybe many of you have not seen that, but because I'm not sure if India has the hops. But I'm sure most of you have drunk beer, right? And the hops is one of the very important ingredient for beer. The flavor of beer basically mainly from the hops. Without hops, there's no beer. But the hops is, when you look at the background here, it's like a vine. It needs to be trained to grow tall so it can grow well and can have a high quality, high yield crop. But to do this training, you need to put a string, put on a very, about a 6 meter tall cables, and then train the vine grow on, up to around the strings. Those work are normally done by human. This is a very tedious and dangerous work, because you can see from here, okay, it's people are standing about 4 meters above the ground, and with the tractor is running in the field, and we know in the field is not like you're running on the concrete. On the field is very uneven. Okay, and if people, the workers do not careful, it may fall down, and then there will be, get injured or even fatal. Okay, plus this is a very, very tedious work. And I myself, before developing this robot, I myself try to do the work to get a feeling how this task looks like to, to human work. I tried about 15 minutes. I did not finish even one knot. And then after this 15 minutes, my arm cannot, I cannot raise my arm for the next 1 week, because you need, when you need to do that, you need to do this all the time. So to release human work doing those tedious, hard, dangerous work, robot is definitely one of the best solution for that. And another issue, it's, I would say, to develop a robot, it's not to say, okay, let's do it when we have time, or let's do it when we do really see the need. And this robot is give you one example, a story, okay? From this story, what is story? This story is a group of WSC research work with local manufacturers to build this asparagus harvester, robotic asparagus harvester. Okay, and Washington State used to be the #1 produced state in US for asparagus. And the US used to be the #1 country to produce asparagus. And so about 10, 15 years ago, actually about 15 years ago, the farmers, they feel like they have a harder time to find field workers to harvest asparagus. Okay, because asparagus is, merges every day. You need to harvest every day for about 2-3 weeks. in a year, only the 2-3 weeks is the window of harvest. So you need to hire a lot of people to do that. And the work is not very easy. It's also very tedious, boring. So about 15 years ago, the industry find out they could not, they have a very hard time to find enough human worker to help them harvest asparagus. So they come to the university, they go to the government and ask for help to develop robotics. So WSA team worked with a private manufacturer to build this prototype. After the 4 or 5 years of hard work, we had this prototype, works fine. Not perfect, but it works. So to make it perfect, I need a few more years for tuning and improvement. However, on the 5th year, which is the second year, no, the 3rd year, I moved from Illinois to Washington, and we were told, okay, stop, you don't need to do it. I was asked why, because over the 10 years period, the industry size reduced about 90%, 90%, simply because they could not find enough labor to harvest. And they cannot wait for the technology to be mature so they can use the technology. Because every year they lost money. The farmers also need bread to feed their family. Every year they lost money, they cannot survive. They just move to something else. So the gross acreage in Washington, it's dropped about 90% from the top in the past 10 years or so. Okay, so this tells us to create robotic technology, we cannot wait to see. Okay, now it's a need, then we start the develop. We need to play-develop. Okay, and even we still have the labor, we need to prepare for it. So this is why what we're doing right now in Washington, we also work with collaborating with university, industry, and manufacturer. We try to develop robotic solutions for apple harvest. Today, the industry, even though there's a challenge to find enough human pickers to harvest the apple, but we still can barely find enough for those years. For this year, looks like it's still okay. Next year, not quite sure, but looks like for the next few years, even though it's tied, we may still go through with it. And the good thing is, this time the industry and the research community is not wait until there's a challenge. Actually, this study was started about 7 years ago. Two manufacturers were involved, actually, different paths. And today, I would say the robotic apple harvester, there are a few different prototypes. I mean, the product prototypes has been tested in the field. Okay, for one developed by Abandoned Robotics, it's not shown here, has been tested in the field for past 4 years. And I believe that technology is very close to be mature for commercialization. And this is from this video here is from FF Robotics, is a company from Israel, based in Israel, and collaborate with us. And for this one, it's been tested for 3 years in the field. Still some issues to be addressed if for commercialization, but I would say in this 3 years of field test, and a lot of technical challenges has been solved. And I would, I would say I would not be surprised if one of those companies start to introduce their early version of a product this year or next year. So this is a good example. If we, prepare early and before the labor issue really hurt the industry, we can provide the robotic solutions as a backup to the industry. So here I give the 5 examples, and the next I was, let's discuss some of the challenges or remaining challenges we need to address. Okay, to talk about the remaining challenges, and I would like to raise your attention, which is the bottom line. Okay, farming basically is a business. Any of the farmers, when they do the farming, they is not only doing it for the farm, they are doing for raise their family. Okay, to feed their family, to raise the family. And so they got to be profitable. And with this bottom line, when we develop robotic technology for agriculture, there are some things, some issues we need to think. We need to always keep in mind. And there are still, if we list the challenges 1, 2, 3, 4, and we can easily list 3 digits of challenges. But with a time limit, I don't think I will have time to discuss all of those challenges. Here, I will just take a few examples and put them into 3 groups. The first group is a technical barrier. And even though after 50 years of development of robotic technology, and even though the robotic technology for many of industrial applications are very mature, very robust and very reliable, but for agricultural application, there are still quite a lot of challenges. And one for the challenge is agricultural operation is at a different season, you need a different operation. For example, in the early spring, you need either seeding or planting. In the growing season, you need either cultivation or spraying or pest control and so forth. And then in the fall, you need harvest. And all those, it's almost equally labor intensive. But those tasks cannot be done by the same machine or the same end effect. And John Deere in a few years ago has tried to address the farmer's request. They have developed a piece of robotic equipment for vegetable growth. And they developed that machine is to address the need of the farmer. But when they introduce the product to the market, they find out nobody buy it. And then why nobody's buying it? After they're doing some survey, they find out, okay, that machine can only take one task of all those field tasks. That means other tasks still requires human being to do it. So that to the particular farmer or they still need to find almost the same amount of human labor to do other work. And while use machine only to do this particular work. And that adds additional cost. Okay, agriculture by itself, profit margin is not huge. If we add additional cost, it goes to economically not sustainable. Okay, so the first challenge for the technical point of view is if we want to use robot for doing agricultural production, you need a fleet of robots to do all of the field work at a different season. Just to use one machine, one robot to do one job and request the human to do the rest. In industry, in manufacturing industry, it is okay. But in agriculture, it is not acceptable. So to develop a robotic solution, you need a robotic solution for the entire operation, not just the one task. That's one major challenge. And the second challenge, the robot for agriculture use needs to be adaptable to all kinds of variations. What I mean all kinds of variations? Okay, let's take a tractor as an example. You know, John Deere tractor is designed and in US, Iowa, you know, Waterloo. After it's been designed, it can be manufactured in US in Moline and then shipped to all over the world, and it works. And however, the field condition in Iowa and the field condition in some place in India could be totally different. But that machine, that tractor, you do not need to make much adjustment or even no adjustment. That machine can immediately work at Iowa farm and at the Indian farm. For robot, can you achieve that? Okay, today's robot, it is a little bit difficult to achieve that. But this is a challenge, a technical challenge you have to address before it can be used. And the third challenge I want to raise, you know, there's many more. I can easily put 300, but here I only raise 3 as an example. The third challenge is the interface of machine with crop. You know, when we talk about industry robot, we only talk about the interface, the human robot interface. Okay, it's not human. You know, here we talk about is the not only human robot interface. In agriculture, other than human robot interface, we also need thinking about human crop interface. Why? thinking about if you pick an apple, the apple picking robot. For a human being, when you see the apple, you can quickly figure out how to reach the apple, how to pick that. And even if there's wind and the branch is waving, you can still easily catch that. But if for a robot, and when the sensor sees the apple at a particular location, and the algorithm calculates the trajectory to guide the end effector from point A to point B to pick that apple. And then there's a wind coming, and then the branch waves, and the apple moves away from your detected position. How do you handle that? Okay, that's one of the challenges we need to address. The second, example for the interface we need to address is, if the apple is growing on a very long and thin branch. For a human, when you see that case, you may use two hands. One hand to hold that branch, and the other hand to pick the apple. But for robot, you may not have the second hand. And the picking of the apple is you create a force to break the stem from the tree. Okay, and then, from the Newton's law, we have the acting force and we have reacting force. So you need to have the resistance to hold that branch so you can create that breaking force. And if for a long, thin branch, your robot grabs the apple firmly and you try to pull it, and the branch will come with you. So you will never create that breaking force. How to address that? This is a very typical crop machine interface issue. And for this, in most of industry robotics, we does not exist in this problem, so we do not need to address that. But for agricultural robot, this is one of the very typical challenge. Okay, and then the next group of challenge is a scale. People always think, okay, use a robot, then we don't need a human. Okay, and my colleagues in China, they said, okay, we can create a humanless farm. I said, no, that's totally wrong. Use of robotics does not mean we do not need a human work. The only difference is the robotic machine is replace human labor to do tedious, dangerous field work. And but we still need a human worker to make the robot work. So instead, to replacing human labor, it is to switch human worker from doing very hard field work to high-tech machine maintenance, programming, supervising, monitoring work. Okay, so raise a high standard for agriculture work. Thinking about that, today, if we have a robot, we put a robot, give a robot to the farmer, say, like give a robot a farmer in India. What do you think? You think that farmer can immediately know how to make that robot work? I'm not sure. At least if for the situation in the US, when we give a robot to a farmer, basically what they do is they just look at me. Qin, make it work. So if we really adopt robots in farm to doing farming work, we need have the skilled workers able to make those robots work properly. This is something we are missing. We cannot send our PhD student to each farm to make the robot work. And a manufacturer, they could not send their engineers to each of the farm to make their product work. So to make the farming society adopt robots, the first thing we need to do is we need to teach the farmers how to operate those robotic machines. So the skills are not there yet. Next, economic barrier. Okay, add a machine means add a cost. Affordability is a big issue. Tractor is more expensive than human labor. Robotics is definitely more expensive than tractor because it has more sensors, controllers, and so forth. It's more sophisticated, it's more advanced. And how to make it cheap enough so farmers can afford it, first place. Afford to buy it. And the second is afford to keep it. Because as I said earlier, agricultural operations have a very short time window. Some operations may only one week a year. Some may be a couple weeks a year to a few weeks a year. But none of the operation will last the year long, either 724 for 52 weeks a year. So normally those machines have very short use time. Very short use time, that means the unit time cost is very high. The third, very important economic issue, challenge is agriculture basically is a year-long operation. So you put the input all the year, you only harvest once. So all the time you have input, and then you only gain from your operation once. What does that mean? That means agriculture is a very high risk operation. Anything go wrong during your entire process, you may damage everything. So that means agricultural production cannot be failed. You failed one operation, you may just get bankruptcy. So the cost is not only the buying. Buying the machine, the cost maybe is small in compare with the overall picture. The cost of buying, the cost of owning it, and the cost of if failed. Those are the things needed to be addressed very well. And then, one solution for that is probably if we do use robot for agriculture, we may need thinking agriculture differently. Why is it differently? Because as I said earlier, the technical challenges, the skill challenges, and the economic challenges. All those challenges makes one solution could address those also challenges is if can we make the robotics as simple as possible. Here is the apple orchard, like apple harvesting. And you can see these trees are totally different from the trees in our imagination. The apple trees in our imagination is definitely not like that. It's a 3D, and it's like a cone shape of a tree. And the apples normally is inside the canopy and so forth. And for the human, we can even climb in the tree and to pick those apples. And can robotic do that? Technically, yes, we can do it. Doesn't matter how complicated the tree is, we can always build a robot to pick those apples from those complicated trees. But that may cause the robotic structure be very complicated, and the control system, the sensing system, everything being very complicated. And the complication increases the cost for build, cost for operation, as well as the cost for failure. So the question here is, since we talk about robotic need to have interaction with human and with crop, and can we simplify the crop? Make the crop suitable for automation. Okay, so this is a challenge, I would say, is one of the major challenges for the research community for agricultural robotics. So as a solution, I would say it requires a transdisciplinary approach. Okay, of course, as agricultural robotics, we have to have robotic science as the core. Okay, it needs to address issues like intelligence, okay, human intelligence, artificial intelligence, collaborative intelligence. Okay, all those intelligence need a computation power. And we need to address the dynamics because the robotic is doing the work. When you're doing the work, there are dynamics involved and the controls. And then probably we also need some biomimetics and actuation technologies. Okay, this is from the robotic technology point of view. And also, we say agricultural robotics. So we cannot ignore agriculture because this is the target of robotic machine is working on. So we need to have knowledge on crop genotyping because of different shape, structure could cause different issues. And physiology definitely address that issue. And then some biophysics. For example, when you use a machine to pick an apple, you need to apply some force to grab the apple. But you need to control that force very well to not damage that fruit. Okay, so the question here is, some varieties could be very fragile, like a Honeycrisp apple. Okay, and then probably we need to create a new variety. It's more sustainable to physical forces applied to there to withstand damage. And then we have robotic science, we have agriculture science, and then probably a very important role is agriculture engineering. Agriculture engineering is a discipline to integrate engineering with agriculture. Okay, this is a critical link element. Without that link, to make robotics usable to agriculture could be very challenging. There are many examples I can tell. Without agricultural engineering help, the tasks were not so successful. Okay, and before end, I have a few comment I want to add. The first is, for agricultural robotics, we should not only look at how advanced the technology is. We need to think about how suitable technology is. For example, this is a robotic bee for pollination. The technology is very advanced. It's a very fancy, very cool technology. But thinking about that, if we use those robotic bee to pollinate 1 hectare of apple trees, how many of those robotic bee you need? In nature, you may need 1 million bees or 100,000 bees. If we say, okay, robotic bee can be more effective and efficient, then we need 10,000 bees, robotic bees. Can you handle the 10,000 robotic bees in 1 hectare field? It is a very, very challenge. So to make the technology usable in agriculture, you should not pursue the most high tech, but you need to pursue most suitable tech. And then, again, just like I said earlier, there's robotic development is a long cycle of research and development. You cannot wait for the last minute to build. If you wait the last minute, the lesson we learned in Washington is the industry will become. The last but not least is we do need a support framework to the farming society with the technology capability, because it will have higher demanding on the scale when we use robotics to the agriculture. Okay, here concludes my presentation. I think I go a couple minutes over. So I believe we will have about half an hour for Q&A, right? And I do see a few people raise a hand, but I try to click that, but I cannot see how can I get those okay answers. And so I would say probably now it's the time to answer, to raise your questions, and I will try my best to answer questions.
Okay. Thank you very much, sir, for delivering an enthusiastic and interesting lecture on agriculture robotics, the need, impact, and strategies. This is very important topic considering the revolution in agriculture as we can say, agriculture is already in its next stage, and therefore, your lecture will definitely be more useful to the students and young researchers who have joined this training program. There are some questions in chat box, and some have raised hands. For the paucity of time, we may not able to take all the questions, but with your permission, I would like to take one important question.
Okay.
Mr. Deepak Kumar, PhD student from Jammu, has a question: how robotics beneficial for small farmers, small and poor farmers, especially country like India?
Okay, this is a very good question. I would say at this point, be honest, it is very difficult for small farmers to adapt the robotic technology. Just thinking about you buying a tractor. When your farm is too small, you may not able to afford a tractor. Say if you have 0.1 hectare, and it's not economical for you to buy a tractor to help you doing farming work. And then when you have a certain size of the farm, then you're buying a tractor, use a tractor will become economical. The same apply to robotics. Okay, if your operation too small, your profit margin may not able to cover the cost. And then the use of robotics will be very challenging. So this is, if you look at the US as an example, US farm in the history used to be also not very big. About 50 years ago, it's like less than 100 hectares. Not hectares, acres. About 10, 20 hectares. And today, the average farm is about 2,000 acres. Increased about 10 times, or more than 10 times. 10, 20 times. Why? Because the mechanization requires more, we call it overhead cost. And those are the costs you need to pay for adapt the technology. So I would say, this is my prediction, no matter which country, consolidation of farming operation is a trend. Again, for India, I'm not very familiar with India. I just only read some articles about India. And you think about India, I think, I'm very much believe India is in the same trend, but maybe, so many years behind US development. Okay, you think about it, 50 years ago, what is the average size of Indian farm? And what is the rural population percentage in India? And today, what is the size, average size, and the population split between the rural population and the urban population? And I think every country in the world is going to the same trend, but it goes more steep or more flat. And this is, I think, is the way it is.
Okay. Thank you, sir. There are still few questions and queries. I'll try to pass on those experts and convey you the response of experts through WhatsApp group or mail. Now, I would like to request Dr. Sachin Nalode, Joint Organizing Secretary of this training program, to propose vote of thanks and introduce our next speaker.
Thank you, Nandalal. And it was a great pleasure to hear Qin It has always been a great experience to hear expertise like you, and all the participants may get better knowledge and sensitization on the robotics, so future of robotics and how we can go forward with futuristic technology. Maybe there are a few constraints which are present in this situation, but those constraints can be overcome. And we will go forward with this particular technology, and we need to think about 10 years afterwards. At least for India, we are making start, and it is good to know this who people like you who are working in this field almost 20 years, and you are getting some results. Maybe those are not directly equal and useful in India, but it is still experience, and we need to know all these things. Actually, thank you very much for your time. You have a busy schedule, and also this is not the official time of US, and you are working in late night hours. So thank you very much from MPKB and greetings from Indian participants, and all over the world there are around 865 participants from 22 countries. So thank you very much for your lecture and guidance to us. Thank you. Thank you. We have a next speaker. We have first was initially it is highly experienced person, and after that young blood. We are having a next speaker who is youngest of all speakers who are speaking in this training program. Engineer Anish Gorantiwar, who is doing his research in US, and currently he is pursuing his research from at the Center for Tire Research. It is at Blacksburg, Virginia in USA, and I know him personally. He is an Indian person who is belong to this state and our city only, and we are related to most of us maybe knowing him. But as a mechanical engineer, he has done his BE and from MIT Pune, and now he has gone for his MS, and continuously he is pursuing as a graduate teaching assistant now in this Center for Tire Research, and working on algorithms for image processing. So this lecture will be helpful for those who want to pursue their career in next few days. Most of the students would like to have this as their new career. So I welcome Anish, and I hope he has joined and he's there. Great.
Yeah.
So welcome, Anish. And
Yeah, I'm here.
copying your father. So it's like Abdul. Best of luck for your lecture, and I hope participant will feel it. This will be energizing lecture. So Anish, please.
Yep. So first of all, hello everyone. Can you hear me?
Yes.
Yes, yes.
Yes. So first of all, I'd like to thank everyone for giving me this opportunity, and especially this platform to talk about some portions of my research. And I believe that after having this conference, after having this talk, most of the students and most of the people, mostly of my age, will basically benefit from this talk, and they'll at least have some kind of idea in while they go in this unmanned aerial vehicle domain. I think I'll just share my screen now. So can you see my screen?
Yes.
Okay, yes.
Yeah,
So,
it is.
okay, thank you. So just to give a short introduction about myself, my name is Anish Gorantiwar, and I'm a graduate researcher in the Center for Tires Research Lab at Virginia Tech. So most of the projects which happen in our lab are basically dependent upon different intelligent tire technologies and mostly on tire wear or friction. But we've started a new kind of project phase which deals with unmanned aerial vehicles as well as unmanned ground vehicles. So for today's talk, I would like to give a brief introduction about the hardware and the software related to the unmanned aerial vehicles and just touch up on some very small and simple algorithms so that everyone can at least get started in this research. So before diving much into detail, I'd just like to give a brief outline of all the topics which we might cover today. So initially, I want to talk about, give a brief introduction about the unmanned aerial vehicles or the drones as it's commonly called. Then I'll overview through different types of UAVs which are commercially present in the market. Then we can basically go to the system architecture. So what I mean by system architecture is we can basically explain all the hardware and the software components which are present in your drone. And then I'll move on to explain different types of hardware, different types of softwares, and how they eventually combine with each other. So what exactly is an UAV? We've heard this term UAV a lot, but many people don't have, even me, I didn't have much knowledge about this UAV field when I first entered it. So UAV essentially stands for an unmanned aerial vehicle or drone as it's commercially called. And it's basically an aircraft which does not have a human pilot on board. So the UAV can either maneuver autonomously or it can be remote controlled by a person who's on the ground. So just to give a small introduction about my research. So I currently work on a collaboration between an unmanned aerial vehicle, which you can see on the top, and an unmanned ground vehicle. And most of my projects are related to combining both of these things for different applications. Okay, so now again, the drones are basically used in wide number of applications. So to start off with, one of the most important and a critical application is the agricultural domain and remote sensing. So the UAVs in agricultural domain are typically used for two applications. One can be basically pesticide or your chemical spraying, and the second one is generally remote sensing. So remote sensing includes basically sensing vegetation and studying different properties of vegetation. The second important application is security as well as emergency responses. So a very critical example in this, which I can give is, for example, whenever there are wildfires which occur, so it's very difficult for humans as such to traverse the entire jungle, the entire forest, and to see where the fire originated or how it's spreading. So this is where the unmanned aerial vehicles and the drones come into the picture. Because of drones, since they have a very high speed and they have good enough flight time, especially the new researched ones, so we can cover large distances in a small period of time. The third application is essentially weather forecasting. Again, this is also a critical application when it comes to in terms of studying different weather patterns, especially wind patterns which occur in a specific region. So in those regions, similar drones can be basically used. And the last but not the least application is basically surveying and mapping. So this is useful when it comes to surveying a particular perimeter or gaining some kind of information about a particular environment or a particular surrounding. And we can take aerial images and see what exactly is going on. So Google Earth, for example, is basically a very critical application of surveying and mapping of UAVs. So I'd just like to give a brief introduction to the different types of the unmanned aerial vehicles or the drones which are commercially available in the market. So we'll essentially go from left to right on the screen. So the first one is basically a fixed wing UAV. So as you can see from the image, the fixed wing is essentially similar to an aeroplane, a normal aeroplane. So its major advantages is, since an aeroplane, it can cover large amount of distances in a very small period of time. But one disadvantage of it is it cannot hover at a particular position. That is, it cannot stay at a particular position for a large period of time. That is why these fixed wing UAVs are not commonly used in some of the applications which I mentioned above. So the next one, and probably the most commonly used, are the multi-rotor UAVs. So the multi-rotor UAVs have a very important advantage that it can basically hover at any particular position. So it can take different aerial imagery and collect data at different points. The next one is a single rotor. So it's basically a subset of your multi-rotor in the sense that single rotor only consists of a single propeller, which moves on an axle. So a helicopter is a very common example of a single rotor. Now, even though the helicopter can also hover, but it's a big downside, or you can say a big limitation of this system is it has a higher complexity in actually moving the helicopter around as compared to the multi-rotors. And the last one, which is currently gaining a lot of importance in the research fields of the UAVs and drones, is a hybrid vertical takeoff landing system. So when I say a hybrid UAV, what does it mean? So hybrid UAV essentially takes out all the advantages of the fixed wing and the multi-rotor, and it combines them together. So this is a very important advantage in terms that the drone can basically fly, as well as it can basically hover at a particular position, as well as it can move forward as well. Okay, so now before diving deep into what exactly a UAV is and what are the different components which are present in a UAV, I would like to give a brief introduction, not an introduction, or basically I want to give a brief application of what are the different subsystems which are present in a UAV. So we can essentially divide the entire UAV into two parts. One is your software system, the software stack, and the second one is your hardware stack. So the hardware consists of all of the different components which are mounted on the UAV. So it might be a camera, a motor, a battery, and basically we'll discuss about each one of these components in individual in detail. But this is what the hardware stack consists of. Then it consists of how can we communicate between one component and another component. And finally, whatever the software algorithms which we do, how do we deploy them on the hardware? And the second subsystem is basically the software stack. So the software stack essentially consists of, again, the different software algorithms. For example, image processing. So if I take an image, what all data can I take from that image? So say I have an image of a vehicle, a building, and a car. So I should be able to identify that this is a building, this is a vehicle, and this is a car. So that is where the perception or the image processing comes into the picture. The second stage is a motion planning. So what motion planning says, you say, for example, I want to go from one point to another point. So as humans, we know how to go through that point because we have our visual perception. That is, we have eyes and we know where the obstacles are. But for a UAV, that is very difficult when it comes to autonomous flying. So that is where the motion planning and the controls come into the picture. So initially, I'd like to give a brief introduction about the hardware structure. So this is just a conceptual design of a UAV to just give all of you an idea of what are the different components which are present and how each and every component communicates with each other. So we'll just start on discussing each one of these components. So the first and the very most important component of the UAV is essentially a flight controller. So the flight controller, you can say, is basically the heart of the UAV. So what the flight controller does, it will take in different inputs from the sensors and it will basically run all the motors which are present on the UAV. The second is a power distribution board. So since we have a battery which is present on the UAV, the power distribution board will help us to route the power from the battery to all the four motors in this case. Then we have the motors. We have the electronic speed controllers, which I'll discuss more in depth in detail. Then we have our propellers, which are essentially used for generating the thrust from the motors. Then we have a GPS, which is a global positioning system. So the GPS basically allows the user to know the position of the UAV in the world coordinate frame, where exactly the UAV is located. So next is a high-level controller. So generally, high-level controllers, you won't see many high-level controllers in commercial drones, but when it comes to research project drones, especially in the fields of agriculture or weather forecasting, high-level controllers are basically used to do different types of software algorithms. So then we have the frame, which forms the base structure, and then we have the battery. So I'll just give a very, very small introduction about each one of these components. So frame, as you know, it basically forms the base structure upon which all the individual components are built. So there are conventionally two types of frames which are available. One you can see is the commercial frames, which can be directly bought from the market. And the second one is a custom frame. So the custom frames generally are dependent upon the user. So say, for example, I'm designing my UAV for pesticide spraying. So for that, I would need to make sure that my drone has sufficient amount of space to say mount my nozzle, to mount the pump, and to mount my pesticide container tank. So that is where the custom frame comes into the picture. Yeah. Now next is the motor propeller. So motor propellers are essentially the main thrust generators of the body of the UAV. So there are a variety of motors available, but the most commonly used are the brushless DC motors, or they're called as the BLDC motors. The main advantage of using the BLDC motors is that they have a very high energy density. That is, for a given amount of current, they can generate a large amount of thrust, and so the UAV can attain a very high acceleration and it can move high up from the ground. So just to give a small keynote here, while selecting a motor, one important parameter to be looked upon is how much thrust the motor can generate, corresponding to how much current it takes from the battery. So as you can see from the graph on the right, as the current drawn increases, the thrust also increases. But the UAV is essentially a cyclic process. You cannot have too much thrust because you'll need a larger battery, and hence the weight of the UAV will increase, and again you'll need different motors. So it's essentially a cyclic process, and we have to start at some point. Okay, so next is the electronic speed controller. Now, in order for the motors to have different speeds so that the motors can move left, right, forward, backward, up and down, it is very necessary that the user can basically control the speed of the motor. So this is where the electronic speed controllers come into the picture. Yeah, the next is the battery. So the battery basically forms the powerhouse of the entire UAV. So commonly LiPo or the lithium polymer batteries are used because they have a very high energy density. So when I say it has a high energy density, it basically means that it can continuously supply sufficient power for a longer period of time. And so important points to be considered while selecting a battery is not only the voltage which it has, and not only the number of cells which it has, but along with that, we basically need to kind of prepare a model. So for example, if I use my battery for say 5 sensors, then how many times will how much time would the battery last? So this is a very important and a critical thing when it comes to UAV design. So if you can see the model on the right, that's a basic simulation model, a software algorithm which I created on MATLAB. And it basically helps the user to know, say, for example, if you're using 10 sensors, then your battery will last 10 minutes. If you're using 15 sensors, then the battery will last only for 5 minutes and so on. Now, the next and most important thing is the flight controller. So as we discussed before, the flight controller essentially forms the heart of the entire UAV. So all the different sensors are connected to the flight controller, and the flight controller tries to manage the UAV. It tries to make the drone fly stable. So you can see it has its own software. So if you can see in the middle figure, you can see 3 green dots which are connected by 3 yellow lines. So those are basically the coordinates where we want our drone to fly. So we just have to select on those coordinates and the drone will fly accordingly. And there was a short animation on the right. So we need to calibrate all the sensors which are connected to a drone so that all of these calibration can be done by the software itself. So this software is essentially called a mission planner software. Now, I gave a brief introduction about high-level controllers. So a common high-level controller is a microcontroller called Raspberry Pi. So what this does is it collects all the data from the flight controller, and all the software algorithms such as the image processing or the motion planning are implemented on this high-level controller. So say you want to drive the UAV autonomously. So for driving the UAV autonomously, we definitely need a high-level controller. So we've talked about all the individual components, but I just wanted to give you a basic flow diagram about how these individual components are connected to each other to form the entire UAV. So as you can see from the figure on the left, for a quadcopter, that is a drone which has 4 motors. We have 4 different motors. We have 4 electronic speed controllers, which are given by ESC. Then we have a flight controller in the middle, a battery, and a power distribution board. And then we also have a transmitter and a receiver for the user who's on the ground and who's controlling the drone. So these are just some of the flight tests videos which I would like to show. So these test videos are conducted in our lab. And one important thing to notice in these videos is it's not always easy to fly a drone autonomously. There are very small critical constraints which many people miss out on. So as you can see in this videos, I hope the videos are clear, but as you can see in the videos, the drone is flying autonomously and it kind of remains steady for some time, but afterward it just loses its track. So because of this, we essentially need to tune a lot of parameters. So now I would like to give so this was the hardware stack, and now I would like to give a brief introduction about the software stack. So, and before moving to the software stack, how does the drone actually move? So just to give a small analogy, we know that, for example, if I'm driving a car, I know I can steer left, I know I can steer right, I can accelerate and I can brake. But for a UAV, it's in your 3-dimensional space. So you should have another motion. So for UAV, there are three different kinds of motion. You have yaw, roll, and pitch. So I'll start from the figure on the left, which is yaw. So this yaw is essentially equivalent to a driver which is steering the car. So I steer left and right. It's the same principle as yawing left and right. The second figure is on the right is basically rolling.
Excuse me, Anish.
Yes.
Your screen has stopped and it is not. Your first slide is only visible to all of us.
Oh, only the first slide.
Yeah.
Okay. I think I'll just share my screen again. Okay, so which slide can you see now?
Battery.
Okay,
Battery.
Yeah. So were you able to see all the previous slides?
Yes, sir. Yes, sir.
Okay, thank
No
you.
problem.
Okay. So as I was saying, I'll just move a bit ahead. Yeah, as I was saying, the aerial dynamics. So we discussed about yaw, then there's roll. So for example, if my hand is the UAV, then roll is basically I'm going towards left and right, left and right. And similarly, we have pitch in which I go front and back, front and back. So these are three important dynamics which are related to a drone. So we talked about all the hardware, but we missed upon important point, which are sensors. So there are different kind of sensors which can be connected to the drones. So just to classify, these sensors can be broadly grouped into two different components. One is your proprioceptive sensors, and the second one is your exterioceptive sensors. Now, these are especially heavy and broad terms, but they have a very simple meaning. So when I say a proprioceptive sensor, it basically indicates sensors which gather information about the UAV itself. So just to give a small example of this, for example, nowadays we see many people wearing Fitbits so they can measure how many calories they burn or what their heart rate is. So that is a very good example of a proprioceptive sensor because it gives information about the bodies itself. So in our case, the proprioceptive sensor gives information about the UAV. The second category is our exterioceptive sensors. So these sensors essentially give us information about the surrounding conditions. And a very good example is a camera. You know, a camera will give you information what is to the front of the drone, left, right, and so on. And there are different kind of sensors, such as camera, LiDAR, and radar. So I would just like to give a much detailed introduction about three important sensors which are commonly used. So first is camera, LiDAR, and an IMU. So cameras, as we all know, they're basically analogous to our eyes. So cameras are used for visual perception. We can correct different kinds of data, and then we can use different data processing techniques. So to say this is a tree, or to say this is a building, that is what all the image processing can be done. The second is your LiDAR, which stands for light detection and ranging. So what LiDAR does is it helps to measure the distance between the UAV and an obstacle in front of it. So to just give a brief idea about how a LiDAR works, so it basically sends light pulses, and then once the light pulses reflect from an obstacle, it comes back to the LiDAR. Then it calculates the time required for the reflected transmitted pulse to come back, and then it calculates the distance. So that is a very simple working principle of a LiDAR. Now, the third and the most important sensor is your IMU. So an IMU stands for an inertial measurement unit, and it is a type of a proprioceptive sensor. So as discussed before, a proprioceptive sensor will give information about the UAV itself. So drone itself. So this IMU will give us information about what is the velocity of the drone or what is the acceleration of the drone and so on. So these are the three most commonly used sensors. Okay, so finally we can dive into image processing. Now we know what all kind of sensors are used for image processing. So I'd like to give a brief introduction about the different techniques which are present in image processing. So we won't be covering all these techniques today, but I'd like to give an introduction to two of those important techniques, which is called as a segmentation and an NDVI imaging. So as you can see from the figures on the right, for example, say you have an edge detection. So you have an original image on the left, and when I apply edge detection algorithms, I can only find this round edge, the edges of the entire UAV. So this is very important when it comes to identifying a tree or a building. I don't have to identify the entire structure, just the outline is also sufficient. Similar examples are a feature detection algorithm. So a very common example for feature detection is, say, for example, I take a picture of a building and then say that building has 10 different windows. So this feature detection algorithm will help me in identifying those different windows. So that is what and these are just very few of like nearly n number of techniques which the image processing has. So before diving into different processing algorithms, there's a very important step which comes into the picture, which is camera calibration. So say I purchase a camera directly from the market. I cannot use this camera as it is. It has to be calibrated. So when I say why do we need to calibrate the camera? So essentially there are some kind of errors which are present in the camera and they are called as distortions. So say with the camera, I take a photo of a straight line. But if the camera is not calibrated, I'll see that straight line as a curved line, which is a very big disadvantage. So that is why we need to calibrate the camera. So we'll start off with one important image processing algorithm, which is called as our NDVI imaging. And this is very, very commonly used and highly used in all of the agricultural applications, especially in remote sensing for the drones. So what NDVI stands for is Normalized Difference Vegetation Index. And it basically is a parameter to see if a particular crop is healthy or it's unhealthy, or if it's basically damaged. So the basic working principle is you can see there's a formula below, and I'll just try to explain in words what that formula essentially indicates. So the formula says that the NDVI is equal to NIR, which stands for near infrared light, minus R, which is basically the red visible spectrum, upon NIR plus R. So to explain in words what this formula is, if you can see the figure on the right, say for example, the left one is a healthy crop and the right one is an unhealthy crop. So whenever light falls on a healthy crop, the infrared light basically falls on the healthy crop. It reflects most of its light. Whereas when visible light falls on it, it doesn't reflect that much amount of light. So using NDVI, we can tell if a crop is healthy or unhealthy. Yeah, so this is just to give a brief idea about how the NDVI values vary with each other. So they can grow from -1 to +1. And say we got an NDVI value of -1. So it indicates the crop is completely unhealthy and it's completely dead, or it's basically an obstacle or a normal object. Whereas if we have an NDVI value of 1, then that indicates that the crop or the entire vegetation is very, very healthy. Okay, so this was just simple image processing algorithms which I was able to do. So the figure on the right, as you can see, that's a normal image, a red, green, blue, or an RGB image as it's called. And the figure on the right is basically your NDVI image. So as you can see from the figure on the left, wherever there are green patches, we basically get correspondingly yellow patches on the NDVI image. And as we go from blue to yellow on the NDVI, the value of NDVI goes on increasing. So we know that the yellow ones have a vegetation, whereas the right ones have either dead crops or they have no crops at all in that region. So this is very important when it comes to application of drones in remote sensing and in the agricultural domain. So one more image processing technique, and that is also commonly used, is called as a semantic segmentation. Again, this is a very heavy word and a lot of research is going on, but I'll just like to give a small introduction to basically explain what semantic segmentation is. So if you can see the figure on the left, the entire road is painted in blue, the car is in green, and the buildings are in red. And you can see the pavement or the sidewalk that is in yellow. So what we can do with semantic segmentation is I can group all the objects which are present in an image into different groups. So I can give group number 1 to roads, for example, group number 2 to buildings, and then it will color all of these individual groups in a single color. So this makes my image processing tasks very easy because I know whatever is in red is a building, or say whatever is a green is in car. So this is very important when I need to maneuver the drone from one point to another point. Okay, so we talked about image processing, basically the perception system. Now I would like to give a small introduction about the control subsystem. Now, I like to give a small analogy which will help you in understanding what control subsystem is. So say, for example, I'm driving a car and I want to take a left turn. And say you're at some high speed, say you're at 40 or 50 kilometers per hour. So I cannot generally directly take a left turn. I'll make sure I'll take a small left turn, then I'll correct it again, take a small and correct it again. So this corrective action which I do, that is the responsibility of the control system. So we know that a UAV has three motions, that is roll, pitch, and yaw. So your control subsystem helps in managing these three motions. So hopefully, I think the video is visible. So you can see this is a small animation which I was able to do in MATLAB. So it basically indicates how good, how well I'm able to control the UAV's different motions. You can see it moves to the left, moves to the right, and then it comes down. So this is what control basically does. I can tell it to go left and right, and it will try to match whatever input I give it. Okay. Now the next subsystem is a motion planning subsystem. So again, I discussed a very little about this and before. So say I want to go from point A to point B, and say I'm driving a car. So mostly as human drivers, we know how to go from A to B. Either we have the routes memorized or we have a GPS system, and we can drive the car. We know if there's a car coming ahead, we can basically avoid that car and keep on moving on the road. But that is not the case for autonomous drones. We have to design specific algorithms so that the drone can move from point A and further it can go basically go to point B. So this is where the path planning and the trajectory generation algorithms come into the picture. So I would just like to just show a brief videos about how the path planning works. I hope the video is visible. So as you can see, the obstacle objects in the green represent obstacles, and the UAV was essentially able to maneuver through these obstacles and reach an open position. So this is one kind of path planning. So the UAV was able to detect where the obstacles are, and it planned its path accordingly. So the next is the trajectory generation. So the difference between path planning and the trajectory generation is the path planning will tell me how to go from point A to point B, but the trajectory generation, that will tell me with how much velocity or how much speed I should go from point A to point B. So as you can see, the shape in blue, which is basically a shape which corresponds to a number 8, that indicates the desired trajectory which I wanted. So as you can see, both the UAVs were not able to get that trajectory in the first step, but as it went on about and about on that same trajectory, it was able to achieve that goal, and it was able to achieve that trajectory. And again, one more example of the trajectory generation is basically, again, following the spiral path. So this is very important when it comes to the agricultural domain, especially pesticide spraying. So see, I have a very big farm or a small farm, and I want to spray pesticides over the entire farm. So what I can do is I can give already a predefined path. So say it's a spiral path, as you can see in the figure on the right, a nearly a spiral path. And I can make the UAV go on that spiral path, and it can basically keep on spraying pesticides. So that is a very common example of a trajectory generation. You can see most of these algorithms are very, very easy to implement. And once these algorithms are implemented on the software through the flight controller and the high level controller, we can easily implement them on the hardware also. So I'd just like to I didn't discuss much about the application of UAVs in the agricultural domain. So as you can see, this is a very small simulation which I was able to do on a software. So it basically indicates the flow pattern of the UAV as it moves around. So the figure on the right indicates where the different nozzles are present for the pesticide spraying. And then the animation on the left, that indicates that how my pesticide spraying will basically affect different crops. So in this case, since I wasn't able to simulate crops, these are basically cuboids. And so you can see how the flow pattern is basically distributed over the entire crops. Okay, I think this was a pretty small presentation. So, but just to conclude, we basically went through most of the hardware setup. Then we covered different image processing techniques. I showed you some videos about flight testing, how that works. And then we went through the motion planning. So how to go from point A to point B and how to control the motion of the UAV. And so all in all, these are only, not all, but some of the algorithms which are used in UAV, and only for some kind of applications. But UAV in general is a very, very vast field. And personally, since I'm also a student, I still feel that I'm learning about UAVs. And the more and more you learn, you feel like there's so much more still left to learn. So with that, I'd like to conclude. And again, thank you everyone for giving me an opportunity. So please let me know if you have any questions.
Okay. Thank you very much, sir. Thank you very much, sir, for delivering a very informative lecture on
Thank you.
unmanned aerial vehicle based image processing algorithm for classification and segregation. This is very important topic, and your lecture will definitely be more useful to the students, young researchers, and practitioners who have joined this training program.
Okay. Thank you so much.
There are some questions in chat box.
Okay, sure.
Okay. We may not able to take all the questions, but with your permission, I would like to take a few questions.
Sure, sure. Yes,
Okay.
definitely.
Soumya Das asked, I have one question. Is this technology relevant for Indian agriculture?
Okay, again, this is a very good question. And so based upon the research which I've done is it's very difficult to implement such kind of technology when it comes to dealing with small scale farmers, because the cost of the entire subsystem in general is very high. So unless these quantities are mass produced, then only basically we can use these technologies in the Indian farming scenario. But again, they're starting to be implemented, and I firmly believe that within 10 or 15 years, these technologies can be implemented in the Indian farming domain as well.
Okay. Thank you, sir. Then Mr. Balaguru has one question. If heavy wind area pesticide application is possible through drones?
Okay, yeah, again, so that is also a very good question. So just to answer that question, so whenever say I spray pesticides or I spray chemicals, two important factors which are to be considered, as you suggested, is the surrounding wind and the height at which I'm spraying the UAV. So both these quantities are basically interrelated to each other. So if I'm able to achieve a smaller height for pesticide spraying, I can somewhat negate the effect of wind. And I can basically, as we discussed about the control subsystem, that is where the controller comes into the picture. So say if I design a very good controller, then it will be able to basically negate all of the basically the motions which are caused by the wind. So say the wind is moving my drone to the right. So with the help of my control system, I can make the UAV move to the left. But again, this is again a very critical, a very fine tuning of the parameter of the algorithm is required. But when you have extremely high winds, then pesticide spraying is very difficult. But for smaller wind speeds, it is definitely possible.
Okay, thank you, sir. Fritz Cameron has one query. How effective or application of UAV in aquatic plants?
In aquatic plants, okay. So again, this is also a very good question. So when you say aquatic plants, like at least as per my understanding, I believe that aquatic plants are based again. So you'll basically need different types of sensors. So a very important sensor which can partially be used is a sonar. So a sonar is basically sound and ranging. So it's similar to a LiDAR, but sonars are commonly used in submarines. So with the help of sonar, we can basically indicate at least where the plants are located. And then right now research is going on to basically make, I don't know the term for it, but basically research is going on to make UAVs which can fly in the air as well as go sub-water as well. So if you have a sonar mounted on the UAV, hopefully we will be able to detect the aquatic plants, and then the UAV in the air can basically go underwater, and if need be, and then it can see what all different, basically it can collect the data for the aquatic plants as well. Again, this is just as per my understanding. I'm not too familiar about the research in this field in basically aquatic plants, but I believe some kind of system can definitely be built.
Thank you, sir. Then Joseph Cameron from Nigeria has asked, which of the image processing techniques is more used actually in agriculture?
Okay, so in agricultural domain, one of the most important image processing technique is the NDVI imaging, which I suggested before. because NDVI imaging is very important for remote sensing as well as pesticide spraying. So for example, since with the help of NDVI imaging, I can identify whether the crop is healthy or the crop is unhealthy, then I will basically tell my UAV to only spray pesticides where I want the pesticides to be sprayed. For example, if the crop is very, very unhealthy and it's nearly about to die, I won't tell my drone to spray pesticides in that region. So I can set different threshold values corresponding to my NDVI imaging. So this is so the NDVI imaging is basically very important image processing technique which is used for UAVs in the agricultural domain. Along with this, I would also like to add an image processing technique which is basically feature detection. So feature detections are commonly used, for example, in the previous presentation, as we saw, for example, for robots, for ground robots which want to collect fruits or something. So that is where feature detection algorithms come into the picture. So as a user or as a robot in general, I need to identify that whether this is a fruit or whatever that object is. So that is where your feature detection image processing algorithms come into the picture. So these are the two main algorithms which I believe are generally used.
Okay. Then Giridhar Usendi adds a question. If sometime occurred any type of diseases in a farm, but don't know farmer know about the diseases occurred or not, that time it is helpful for monitoring the diseases.
Okay, again, so this is also a very, very good question. So I'd like to answer this question by just giving a very little background about how to tackle this question. So this is where machine learning basically comes into the picture. So what machine learning will tell you, say for example, I've already collected the data for 3 diseases which occur in the plant. So I know if disease A occurs in the plant will look like this. If disease B occurs in the plant, it will look like this. And if disease C occurs in the plant, it will look like this when I take its photo with the help of a camera. So if I already know what all the possible diseases which can occur, then by using camera and different image processing techniques, I can identify if I take a new picture of a camera, then by matching it with all the data which I already have, I can say that this plant has this disease or this plant has this disease. But the main I won't say drawback or the main limitation of using such an approach is that we need to have a very high data set, very large data set. That is, we need to cover all of the diseases present and corresponding to all of these diseases, how different crops look like. So this is again just one of the approaches to go for this, but I'm pretty sure there must be other approaches as well. But machine learning is one of the approaches.
Okay. And I ask last question.
Sure.
Dr. Shyamrajan Das from ICR New Delhi asked, which UAE is appropriate for precision farming?
Okay. So in basis of for commercially brought UAVs, I believe that there's a company called DJI Phantom. And so, yeah, it's DJI and I. So DJI has recently started production of UAVs and drones, which are very, very specific to precision agriculture. So the applications which those drones cover basically lie from either, as I said, pesticide spraying or chemical spraying up to remote sensing as well. So these drones are basically the forerunner, if you can say, in the precision agricultural field for the drones. So I'd suggest the DJI, if you can, these drones are commercially available as well. So you can just search for DJI Phantom drones, and those are the most. There are many other drones as well, but these are the most commonly used for precision agriculture.
Okay, thank you very much, sir, for the information of all the participants. There are still few questions and queries in chat box.
Sure.
We shall try to pass on those to the experts and convey you the response of experts through WhatsApp group or email.
Okay, sure, definitely.
Okay, thank you very much, sir. Now I would like to request Dr. Mukund Shinde, sir, organizing secretary of this training program, to propose vote of thanks.
Very nice and introductory lecture on drones, fundamentals of drones. There are more than 800 participants, and I believe most of them are very new to this technology. And we are sure that all of them are very happy and satisfied the way you deliver explain the fundamentals of the drone technology. And it's bit applications for agriculture, precision agriculture. And let us hope to meet you again. And
Oh, yes, definitely.
yeah, congratulate on behalf of MPKV Rauri and the CAST project.
Oh, no,
So,
thank you so much. Thank
very
you.
nice lecture.
Okay, thank you so
And
much.
all the
Thank
best
you.
wishes. Thank you.
Yes, thank you. Thank you.
Okay. Thank you very much, Dr. Sinde sir. Before we end the session, we have few announcements. In spite of our repeated appeal and guidelines, some of the participants have not joined by their names, followed by name of organization to which they belong. This is important for recording your attendance during the sessions, to recognize their registered participants, and also for a security purpose. If found tomorrow not joined by their names, followed by organizations, will be removed. They have, however, the option of joining YouTube. As informed in beginning, we shall post one short assignment on a WhatsApp group at 4 p.m. at Indian Standard Time. All participants are requested to submit the assignment on time and as per the guideline issued on WhatsApp group and on time. Please note that responding to this assignment will be considered for issuing the certificates to the participants. So thank you very much. With the permission from co-convener, we would like to close the session. So see you tomorrow at 4:45 a.m. Thank you one and all.
Nandlal, before closing, please make announcement that tomorrow's session, when it will be starting and when this participant has to join.
Okay, sir.
Nandlal, can you hear me? Please make announcement that when that session is, because today's session was 15 minutes earlier.
Yes, sir. Yes, sir. Today we have two sessions, and we will start at
Tomorrow.
9 a.m.
Tomorrow's session is at 9 a.m. India. So accordingly, you can organize your calendar, and others who are participating from other countries. So it is 9 a.m. India time. It will start tomorrow. Thank you.
Okay.
Yes.
Okay, sir. Shall we end the meeting?